Every submarine built before 1959 was designed wrong. Not poorly designed, not inefficiently designed, but fundamentally wrong at the most basic level of how a submarine should move through water. Engineers knew this. They understood the physics. They could calculate exactly how a submarine hull should be shaped for optimal underwater performance. But they built submarines anyway, using hull designs inherited from surface ships. Designs optimized for operating on the surface rather than beneath it. Because until nuclear propulsion arrived, submarines had no choice. They were surface ships that could temporarily submerge, and their hulls reflected that reality. USS Skipjack changed everything. She was the first submarine designed from the keel up to be a true underwater vessel, and her revolutionary teardrop hull form became the template for every modern submarine that followed. The story of how this happened is the story of engineering finally catching up to physics, and of one submarine that proved a theory so thoroughly that it rendered every previous submarine design obsolete. Submarine hull design from the earliest vessels through World War II followed a consistent pattern. The hull was essentially a surface ship hull, long and narrow, with a flat or slightly rounded bottom and a deck structure on top. This design made sense for vessels that spent most of their time on the surface. A long, narrow hull moved efficiently through surface waves. The flat bottom provided stability. The deck structure gave crew members space to work when surfaced. But underwater, this design was hydrodynamically terrible. Water flowing past a long, narrow hull created enormous drag. The flat surfaces and sharp angles disrupted smooth flow, creating turbulence that slowed the submarine and required more power to maintain speed. The deck structure and conning tower acted as massive speed brakes underwater, forcing water to flow around obstacles rather than smoothly along the hull. Engineers during World War II understood that a better underwater hull shape existed. Extensive wind tunnel testing and theoretical calculations showed that a teardrop shape, fat in the middle and tapering to points at both ends, moved through fluid with minimal drag. This shape allowed water to flow smoothly along the hull without separation or turbulence. A submarine with a true teardrop hull could achieve much higher underwater speeds with the same amount of power, or achieve the same speeds with less power and therefore quieter machinery. The physics were clear. The advantage was undeniable. But implementing this design on actual submarines faced seemingly insurmountable practical problems. The fundamental issue was that diesel-electric submarines needed to operate on the surface regularly. They surfaced to run their diesel engines, to charge batteries, to transit at higher speeds than their submerged battery power allowed. A teardrop hull was terrible for surface operations. The rounded bottom provided poor stability in waves. The lack of a flat deck made surface operations difficult and dangerous for crew members. The hull shape that was optimal underwater was nearly useless on the surface. So submarine designers compromised, building hulls that worked adequately in both environments, but were optimal in neither. This compromise persisted through World War II and into the early Cold War because the operational requirements left no alternative. Nuclear propulsion eliminated the compromise. A nuclear submarine never had to surface, except to load supplies and change crew. The reactor ran continuously, providing unlimited underwater endurance. There was no need to surface for battery charging or diesel engine operation. This meant the hull could be optimized entirely for underwater performance, without any consideration for surface characteristics. The teardrop hull suddenly became practical. You could build a submarine shaped like a teardrop, knowing that it would operate submerged essentially all the time, and the terrible surface characteristics wouldn't matter because the submarine would rarely be on the surface. The United States Navy had commissioned USS Nautilus in 1954, proving that nuclear propulsion worked in submarines. But Nautilus used a traditional hull design, long and narrow with a conning tower and deck structure, because she was designed before engineers fully committed to the teardrop concept for operational submarines. Nautilus was revolutionary in propulsion, but conservative in hull design. The next generation will be revolutionary in both. The Navy authorized design work on a new class of attack submarine that would combine nuclear propulsion with a teardrop hull that physics demanded. This submarine would be faster underwater than any previous submarine, more maneuverable, and would establish the hull form that every subsequent submarine would follow. USS Skipjack's design began with a clean sheet and a single guiding principle: optimize everything for underwater speed and maneuverability. The hull would be a true teardrop, maximum beam near the middle, tapering smoothly to points at bow and stern. No deck structure, no conning tower projecting above the hull, just a small sail integrated into the hull shape to minimize drag. The control surfaces, rudder, and diving planes would be positioned for maximum effectiveness in high-speed underwater maneuvers. Every external surface would be smoothed to reduce drag and noise. Nothing would compromise the hydrodynamic efficiency of the design. The engineering challenges were substantial. A teardrop hull is inherently less stable than a traditional hull. It wants to roll. Keeping the submarine level required sophisticated control systems and careful weight distribution. The absence of a traditional deck structure meant that all systems had to fit within the pressure hull itself, creating space constraints that traditional submarines didn't face. The smooth external surfaces required new construction techniques to eliminate the rivets and protrusions that traditional submarines had used. And the entire design had to be built and tested before anyone really knew if the theoretical advantages would translate into practical operational capability. If you're enjoying this exploration of how submarine design evolved during the Cold War, make sure to subscribe. Every week, we cover the engineering breakthroughs, strategic decisions, and human stories behind the submarines that shaped naval warfare. Construction of Skipjack began at Electric Boat in Groton in 1956. The shipyard workers faced challenges they'd never encountered before. The teardrop hull required new welding techniques to create smooth, continuous surfaces. The tight internal spaces demanded precise placement of every system and component. The sail, which housed the periscopes and surface navigation equipment, had to be integrated into the hull shape rather than sitting atop it like traditional conning towers. Every aspect of construction required rethinking traditional submarine building practices. Skipjack was commissioned in April 1959, and the Navy immediately began sea trials to validate the design. The first submerged speed runs produced results that stunned observers. Skipjack was fast, dramatically faster than any previous submarine. The exact speed remains classified, but it exceeded 30 knots submerged, nearly double the speed of most earlier submarines. More importantly, Skipjack accelerated quickly, turned sharply, and maneuvered with agility that no previous submarine could match. The teardrop hull delivered everything the physics had promised. Underwater, Skipjack handled like a fighter aircraft, responsive and precise, capable of maneuvers that would have been impossible for traditional submarine design. The strategic implications became clear immediately. The Cold War was heating up, and a critical component of that competition was underwater. Soviet submarines operated in the Atlantic and Pacific, threatening American naval forces in coastal cities. American submarines tracked Soviet vessels, gathered intelligence, and maintained deterrent patrols. The underwater environment was becoming a battlefield, and in that environment, speed and maneuverability meant survival. A submarine that could outrun and outmaneuver opponents had decisive advantages in both offensive and defensive operations. The Soviet Union had not been idle while American engineers developed the teardrop hull. Soviet submarine designers understood the same hydrodynamic principles, and they were working on their own high-speed submarines. The November-class nuclear attack submarines, which began entering service around the same time as Skipjack, represented the Soviet answer to American nuclear submarine development. These submarines were fast by the standards of their era, crude in some respects compared to American boats, but formidable nonetheless. The underwater arms race was accelerating, and both sides understood that the nation that fielded the faster, more maneuverable submarines would have significant tactical advantages. American naval strategists looked at the emerging Soviet submarine threat with genuine concern. The Soviets were building submarines in large numbers. Soviet naval doctrine emphasized aggressive operations close to American coasts and shipping lanes. If Soviet submarines could operate with impunity because American submarines couldn't catch them or outmaneuver them, the strategic balance would shift dangerously. The Navy needed submarines that could match or exceed Soviet capabilities, submarines that could hunt Soviet boats in the Atlantic and Pacific, submarines that could protect American carrier battle groups from underwater threats, submarines that could maintain surveillance of Soviet naval operations without being detected or evaded. Skipjack proved that such submarines were possible. Her speed meant she could pursue Soviet submarines that tried to flee. Her maneuverability meant she could track targets through evasive maneuvers. Her hydrodynamic efficiency meant she could operate quietly at speeds where other submarines generated noise that gave away their position. In exercises against other American submarines and in operations tracking Soviet vessels, Skipjack demonstrated capabilities that validated the entire teardrop hull concept. The submarine that had been revolutionary in design proved revolutionary in operation. The Navy's response was to build more. 5 more submarines of the Skipjack class were constructed, each incorporating minor improvements but following the same basic teardrop hull design. These submarines formed the core of American attack submarine capability in the early 1960s. They operated aggressively, tracking Soviet submarines, gathering intelligence, demonstrating American capability to operate anywhere in the world's oceans. The Skipjack class established American submarine superiority during a critical period of the Cold War, the years when both superpowers were developing their underwater forces and establishing the patterns of operation that would persist for decades. But Skipjack's influence extended far beyond her own class. The teardrop hull had proven itself so thoroughly that it became the standard for all subsequent submarine designs. When the Navy designed the Permit class, commissioned starting in 1961. They used a refined version of the Skipjack hull. When the Sturgeon class followed, they used the same basic shape, with improvements for deeper diving and quieter operation. The Los Angeles class, commissioned starting in the 1970s and eventually becoming the most numerous nuclear attack submarine class ever built, used a teardrop hull that traced its lineage directly to Skipjack. The Seawolf class and Virginia class submarines that followed continued the tradition. Every American nuclear submarine designed after Skipjack has used some variant of the teardrop hull that she pioneered. The Soviet Union followed a similar path. After encountering American teardrop hull submarines and recognizing their advantages, Soviet designers adopted the same basic principle for their own submarines. The Victor class, Akula class, and later Soviet submarine designs all used teardrop hulls. The hydrodynamic advantages were too significant to ignore, regardless of political ideology or national origin. Physics dictated hull shape, and physics didn't care which flag a submarine flew. This convergence on a single hull design created an interesting situation. By the 1970s, American and Soviet submarines looked remarkably similar in basic shape. Both used teardrop hulls, both positioned their control surfaces in similar locations, both adopted streamlined sails. The differences were in details: propeller design, internal arrangements, reactor types, sonar systems, noise reduction technologies. But the fundamental hull form that Skipjack had pioneered became universal. Every Navy that built nuclear submarines adopted the teardrop hull because no alternative offered comparable performance. Modern submarine design has refined the teardrop concept but never abandoned it. The Virginia-class submarines currently being built for the United States Navy use a hull form that would be instantly recognizable to Skipjack's designers. The proportions have been optimized, the external surfaces are smoother, the materials are advanced, but the basic shape remains a teardrop. Maximum beam near the middle, tapering to points at bow and stern, minimal protrusions, everything smooth for hydrodynamic efficiency. This is Skipjack's legacy, visible in every submarine launched over the past 6 decades. The technical lineage is direct and unbroken. Skipjack proved the teardrop hull worked. Permit refined it for deeper diving. Sturgeon improved noise reduction. Los Angeles increased speed and capability. Seawolf pushed quieting to new levels. Virginia incorporated modular construction and advanced sensors. But all of them, every single one, used the hull form that Skipjack validated in 1959. The evolutionary path from Skipjack to modern submarines is continuous and clear. Each generation built on the previous generation's achievements, but All of them trace back to the revolutionary design that Skipjack represented. Skipjack herself continued operational service through the 1980s, eventually being decommissioned in 1990 after over 3 decades of operations. She conducted countless patrols, tracked numerous Soviet submarines, participated in exercises and operations that demonstrated American submarine capabilities. Her crew members, rotating through over the years, learned submarine operations on a platform that had established the standards for all submarines that followed. The techniques developed aboard Skipjack, the operational procedures, the tactical approaches to submarine versus submarine combat, all of these became doctrine that subsequent submarine crews inherited and refined. The submarines that succeeded Skipjack were larger, quieter, deeper diving, more heavily armed, equipped with more sophisticated sensors and weapon systems, but none of them were fundamentally different in the way that Skipjack had been fundamentally different from everything that came before. Skipjack represented a discontinuity, a break with all previous submarine design philosophy. Every submarine after Skipjack was a refinement, an improvement, an evolution. The revolution had already happened. Skipjack was that revolution. Consider what submarine design would look like if Skipjack had never been built, if the teardrop hull had been abandoned or never pursued. Submarines would still have nuclear propulsion. They would still be capable of extended submerged operations, but they would be slower, less maneuverable, noisier, less effective as tactical platforms. The underwater competition between American and Soviet forces would have evolved differently. The capabilities that modern submarines take for granted, the speed and agility that allow them to operate effectively in contested waters, would be absent or diminished. Skipjack didn't just improve submarine design. She established the paradigm that all subsequent design followed. The engineers who designed Skipjack, the shipyard workers who built her, the crew members who operated her, all of them contributed to changing naval warfare, as fundamentally as the introduction of steam power or armor plate had changed surface naval warfare in previous centuries. This wasn't incremental improvement. This was transformational change, the kind that happens rarely and defines everything that follows. The teardrop hull was not a new feature added to submarines. It was a new conception of what a submarine should be, how it should move through water, what it should be capable of doing. USS Skipjack was scrapped in 1996, cut apart at Puget Sound Naval Shipyard. Her reactor compartment was removed and sent to Hanford for burial alongside dozens of other decommissioned reactor compartments. The physical submarine is gone, but walk through any modern submarine, American or foreign, nuclear or conventional, and you're walking through a descendant of Skipjack's design. The hull shape that surrounds you, the way the submarine moves through water, the capabilities it possesses, all trace back to the decisions made when Skipjack was designed. In the history of submarine development, certain vessels stand out as transformational. USS Holland demonstrated that submarines could be militarily useful. German U-boats proved they could be strategically decisive. USS Nautilus showed that nuclear propulsion worked in submarines. USS George Washington proved that submarines could carry ballistic missiles and provide invulnerable deterrence. USS Skipjack established how submarines should be shaped. Each of these vessels contributed something essential to modern submarine capability. Skipjack's contribution was fundamental. She proved that submarines should be designed for underwater performance above all else, and she demonstrated the hull form that optimization demanded. The teardrop hull is now so standard, so universal, that it's easy to forget it was once revolutionary. Every child's drawing of a submarine shows a teardrop shape. Every movie depicts submarines as streamlined vessels tapering to points at each end. The image is so embedded in popular consciousness that it seems inevitable, as if submarines could never have looked any other way. But they did look different. For the first half-century of submarine development, submarines looked like surface ships with the ability to submerge. Skipjack changed that image permanently and completely. The Cold War produced many technological innovations driven by military competition. Some of these innovations were expensive but ineffective, dead ends that consumed resources without delivering meaningful capability. Others were effective but specialized, useful for specific missions but not broadly applicable. A few were transformational, changing not just military capability, but the fundamental understanding of how weapon systems should be designed and operated. USS Skipjack's Teardrop hull falls into this last category. It was a genuine breakthrough, proven effective, universally adopted, and still relevant over 6 decades after the first Teardrop submarine entered service. The men who served aboard Skipjack probably didn't think of themselves as participants in a revolution. They were submarine sailors doing their jobs, standing watches, maintaining systems, executing operations. But they were operating a platform that established standards every submarine that followed would meet or exceed. The maneuvers they practiced became the basis for submarine tactics. The speeds they achieved became the benchmarks for subsequent designs. The capabilities they demonstrated became the requirements for future submarines. Skipjack's crew contributed to submarine development not through research or engineering, but by proving that the revolutionary design worked in operational conditions, that the theoretical advantages translated into practical capability. Today, when submarine designers sit down to create the next generation of underwater vessels, they start with the teardrop hull. They might modify proportions, adjust the exact shape, incorporate new materials or construction techniques, but the fundamental form remains Skipjack's teardrop. This is the ultimate validation of a design. Not just that it worked when new, but that it continues to work decades later, that no alternative has proven superior, that refinements and improvements preserve the basic concept rather than replacing it. USS Skipjack was the submarine that proved physics right. She demonstrated that hydrodynamic efficiency mattered more than tradition, that optimal underwater performance demanded a specific hull shape, regardless of how radically different it looked from previous submarines. She established the template that modern submarines still follow, because that template remains the best solution to the problem of how to move a large vessel through water quickly, quietly, and efficiently. This is Skipjack's legacy. Not just a successful submarine, but the submarine that showed every other submarine how to be designed.